We'll be studying serial links, which involves looking at digital data transmission and bit error rates and so on. So to calculate these things like bit error rate, we need to know some things about random processes and noise, like I mentioned yesterday. So we'll have a quick primer on those things. This is not meant to be a complete treatment, but just enough to carry out the calculations that we want. Okay. These things will be done more completely if you take a course on probability and random processes or some rigorous course on communications and so on. Okay. So before we get into noise, I mean, of course, all of you know about deterministic signals, where essentially you know the value of the signal exactly, right? Now there are so many of examples. This is the kind of signals that you would have seen or etc. Right? As a function of time, you know the value of the signal. You know the value of the signal at every instant of time. Okay. In general, the variables that we deal with are signals, which means they have some values as a function of time, and we operate. I mean, the circuits that we have operate on those signals. Okay. Now, in case of random process, so let's say we have a random process X, like I mentioned, so X could be a signal as a function of time. This could be a noise in a resistor, for instance. You measure the noise in a resistor, it goes on varying. Also, it's a signal of a plot that can be plotted as a function of time. Now, the distinguishing feature with about a random process is that you can have an ensemble, you can have many instances of the same experiment. For instance, it could be that you have many 1 kilo ohm resistors and you measure the noise in each one of them. Okay. So what happens is that each instance will in general have a different value. So these are all basically different instances of the same random process. Okay. Now this is in contrast with, let's say, a deterministic process. I mean, as a sort of crude example, I'll take a battery. If you take like many batteries, they'll all have the same voltage, right, as a function of time. I'm not including noise here, obviously. But if you take resistor noise, for instance, so one of them may be something like this, the other one may be something different. It will be in general something different, and third one will be yet another, third one will have yet another different value and so on. Okay. So now what can we say about this? We clearly cannot say X as some known function of time like this, right? Because every time it's going to be something different, every instance is different. So like I mentioned yesterday, what you do is, it's not as though we don't know anything about it either, okay, in random processes. So for instance, let's say you take a particular instant of time, let's say I call this T naught, this, and you look at the values of these different instances. This is x1 of T naught, this is x2 at T naught, and x3 at T naught, and so on. Okay. So now you look at the values of all these different instances of this random process at some particular instant T naught. And let's say you plot their distribution, histogram. You know what a distribution is, right? So when you have this is the value of x. and let's say you subdivide into bins. I mean, you know what a histogram is. So you have many instances here. You look at how many instances have value that falls in this bin and how many instances that have values that fall in this bin, how many instances fall in this bin, and so on. So that's what a histogram is. Okay. Now when the values are continuous, right, when they can take on any value, essentially you make the bin width to be 0 and you plot what is known as a probability density function. Okay. So it could be something like this. I will draw it like this because this happens to be the most frequently seen type of distribution. So this is known as the probability density function. What it means is that if you have some x naught, right, and then you have a, let's say, really tiny bin of width delta x around that x naught, then the probability of this x taking a value within this band is how much? It's the probability density function at this point times delta x. Okay. So by the way, in the histogram you plot the number of instances you see in each bin. Okay. And if you divide those, divide that by the total number of entries you have, okay, the sum will become 1. So then it shows the probability, right? You understand what I'm saying? So maybe you do this experiment a million times and then you find that maybe 100,000 times it's here and then it goes on reducing like this, right? And then the sum of all these bin values will be the total number of instances that you have. Okay. Now if you divide this by the total number of instances, the sum will become 1 and each of these bin heights represents the probability that it is going to be in that bin. Is that okay? Each instance is, what do you mean by that? Each instance has some values, yeah. Yeah. Okay. So we describe the probability density function, the probability that it is going to be somewhere, right? It can take on any value, but it's not something unknown. Typically, you know what the distribution is. Okay, I'll come to this Gaussian distribution later, but it will be something like this. And what you do with this probability density function, from that you can find out if, let's say, if you want to find out, let's say, what is the probability of x being between, let's say, 0.5 and 1. How do you find this? This x is, let's say, between 1 and half. How do you find this now? You have to basically find the, you have to look at where, let's say, 0.5 is and where 1 is and look at the area under it. Okay, so that gives you the probability that this x takes on a value between half and 1. Okay. And obviously, if you integrate over all values, what will you get? 1. So that means that x will be obviously somewhere in between minus infinity and infinity. So these things you know from basic probability stuff, right? Now there are some variants of this. I drew signals versus continuous time, right? At every instant of time it has some values. But it could also be a sampled signal. I mean, you could have a random process, but that is defined at discrete instants of time. And this again happens in our case, for instance, you have bits. You have basically bits as a function of the discrete index n, and the bits can have random values. I mean, not just bits, but also symbols and so on. Okay. So if you take multiple instances of this random process, I mean, for instance, in this case, the random process could be, let's say, the bit stream sent by a person's mobile phone versus somebody else's mobile phone versus somebody else's mobile phone and so on. Each one will be sending, I mean, we can say that they are like a random sequence of bits, and they also will be in general different from each other. It will not be the same. Okay. So this is just a minor variant. Instead of each instance being a continuous time signal, it's a discrete time signal. That's all. Okay. And the examples are something. It can be anything, right? Some stuff that like this. This is, let's say, x1, x2, x3 and so on. And this makes no difference as far as what we were saying earlier is concerned. So you take some n equals n naught, and then you look at x1 of n naught, x2 of n naught, all these values, right? xn of n naught, and you can plot their histogram. If you have a finite number of these things, you will get something, or you can normalize it to the total number of entries and plot the probability density function. So that also can be something like this, right? Okay. So basically this the x-axis of this process could be continuous time or discrete time, but at each instant of time there will be some distribution. Is this okay? Then on top of it, these values themselves could be either discrete valued or continuous valued. Okay. For instance, if let's say this was representing successive coin tosses, right? x1 represents, like I go on tossing coins, let's say once every second or once every 5 seconds. So that sequence is x1, and then you do it, it is x2, somebody else does it, it is x3 and so on. So in this case, these values also will be discrete. Okay, it has only two possible values, +1 and -1. Let's say heads and tails are +1 and -1. So there also there will be some distribution. If you take any particular sample number, any particular instance, there will be some distribution. What will the probability density function of that look like? And let's represent -1 is tails and +1 is heads, let's say. What will the probability density look like? Two Gaussians. Why? I mean, if you have a Gaussian, so that means that it is at -1, but also it can be somewhere here, right? Yeah. So in this case, if you draw the probability density function like this, this is now a function of this continuous variable x, right? Okay. So now x can only take values of -1 or +1, head or tail. Okay. You have seen functions like this, the functions which have, I mean, sort of functions which have values only at one particular instant, right? What is that function? The impulse. So for instance, here it will have two impulses because it cannot possibly take any other value. It can only be either head or tail. Okay. So if you say you are going to write the probability density function of this coin toss, it can have only values here and nowhere else. And of course, if it's a fair coin, these two probabilities will be equal. What will be the area of each impulse? 0.5. So basically, this is half delta of x plus 1, and this is half delta of x minus 1. Now again, the probability that it's a head, how do you find out? you will integrate just between, let's say, just below plus 1 and just above plus 1. You will get an area of half. Okay. Similarly here, you will integrate from just below minus 1 to just above minus 1. You will get an area of half. So this means that probability of tails and heads are both half. I mean, there's nothing here that you don't already know. You already know that probability of heads and tails are half. But all I'm showing is, if you plot the probability density function as a function of, and if you make this x a continuous variable, this is what you will see. Now, when it is discrete valued, you don't have to represent it like this. You can also, you know that the values are discrete, and you can plot simply the probabilities of these discrete numbers, minus 1 and plus 1 and 0 and so on. Okay. So then this will be half and this will be half, and that's it. Okay. Is this clear? This is again like the continuous time versus discrete time signal. If you have a continuous time signal, you will have to have a value at you have to have some value for the function at every value of time. Whereas if you have a discrete time function, then it's only at some discrete instances. Similarly, the probability also can be represented as a density function of a continuous variable, or you have a discrete independent variable, and then you simply write the probabilities for each of those values. Is this okay? I mean, the reason I'm introducing all this is we will see all of these things in references related to serial links. Okay. Now, for instance, if you have a throw of dice, right, and you plot the probability density function as a function of this continuous variable, where x is basically the value that you see on the dice. What will the density function look like? It will have 6 impulses, right? So, and again, a fair dice means they'll all have the same areas, and each of them will have an area equals 1/6. Okay. So similarly, we'll come to the distribution of noise and other things later, but you will have some probability density function. The density functions can be continuous or discrete. Again, we will see examples of both. For instance, if you have a random bit stream that is coming out, that's exactly like a coin toss. It will have equal probability of being minus 1 or plus 1, and the probability density function looks exactly like this. Is this okay? Any questions so far? Now, here I looked at the distribution at T0. Maybe I can look at it at some other instance T1 and plot its distribution. So this is for at T0, and at T1 in general you could get a different distribution. Okay, it's not necessary that they will all be the same, but it turns out for a lot of processes that we have, it will be the same. Okay. Again, you can think of either the coin toss or dice throwing. So let's say we all decide to do this experiment together along with maybe a million other people. Let's say every 5 seconds we toss a coin or throw a dice. Now you feel that, okay, this distribution is not going to change with time, right? I could take it at this instance, or maybe the 5th coin toss or the 10th coin toss. All of them will have the same distribution. That is, they'll have equal probability of being heads or tails. This is not necessarily the case for every kind of signal that we will see. Okay, but for things like resistor noise and so on, if you look at this instant or that instant or some other instant and plot the distributions, they will be the same. Okay, is this fine? So in fact, a lot of practical cases we will look at. and this kind of a process is known as a stationary process. Again, I am being very unrigorous here. There are some rigorous definitions of all these things. So if it's a stationary process, so that means that you look at the distribution now or later, it will look the same. Now, while this is quite common, this is not necessarily universal. Okay. In particular, there are a couple of processes that we will see which will be non-stationary. That is, you look at the distribution now or later, it will be different. And there is one kind of time variance that is quite common, time variation that is quite common. That is, because we have signals which are driven by clocks, right? Okay. If you know anything about digital circuits or any circuit, what will happen is that this clock, this kind of clock or any large periodic signal will put different parts of the circuit into different states. For instance, you could have switches operating from this clock. So maybe the switch is on in this part and switch is off in that part. Okay. So this is again quite common. Or if you know the schematic of a CMOS inverter, and then if you drive it with this clock, you know that during the high period the NMOS is on, PMOS is off, and during the low period it's the other way around and so on. Okay. So because of this periodic switching action, the circuit will behave differently during different parts of the cycle. Okay. So in such circuits, it is not true that at every instant of time the distribution will be exactly the same. Okay, they can be different in different parts of the cycle. And so in general, of course, they could be varying in some arbitrary way, but one very common type of variation is this periodic variation, and the periodic variation comes because of the clock. It could be that near the clock edges you have a lot of noise, and then when it is flat you don't have that much noise. This is one type of variation, but anything can happen. So basically it means that within this period, so you plot the distribution here, you get something which is related to this T1, and then at T2 you get a different function. Okay, and at T3 you will get a different function and so on. Okay. Now once the period is over, then the same pattern repeats. Within each period it will have different let's say different probability distribution at probability density function at every instant of time. Okay, and it repeats, and this type of stuff is known as this type of stuff which has periodic variation of Px or probability distribution. This is known as a cyclostationary process. By and large, everything that we do calculations with will be stationary, but these things are also, the cyclostationary stuff is also common enough that you should be aware of its existence, and sometimes you will have to take into account the fact that the noise will be different at different instants of time. Okay. This is fine. So again, we have not gone into any specific circuit, but you can imagine that if the clock is operating from switches, the circuit could be one way in when the clock is high and in a different way when the clock is low. So they essentially have two different circuits when the clock is high and low. So that means that you could potentially get different values of noise. And similarly, the transistors could be in different operating points when the clock is high and when the clock is low. So you could get different types of noise and so on. Any questions so far? So we will consider stationary processes for now, but we should be aware that there are the cyclostationary processes where the probability density function will be periodic, right? Fine. Essentially all I am doing is to introduce the basic definition so that we can use these things. Now let's get back to the stationary process for now, right? And you will have some probability density function. and it will have some shape like this. Okay. So this, as you know, is the sort of average value. You want to see what the average value is. So you weight it by the probability density function and integrate it. This is denoted by this E stands for expectation. But from this definition itself, you know that this is basically the mean value, right? This is the mean. And again, for a stationary process, the mean will be same at every instant of time. Okay. Now, in our case, right, when we deal with noise and so on, we will be dealing with zero mean processes. What actually happens is, so let's say, okay, let me, this is the mean of x. So let me define a new random variable, which by definition is x minus e of x. That is, I subtract the mean from x, okay, and I plot the probability density function of y as a function of y. What will that distribution look like? What happens to this? So it will get shifted to, I have just subtracted that value, right? Whatever value I subtracted from, it will get shifted by that value, okay? And what will be this number? What will be the expectation of y? What will this be? It will be by definition 0 because I have subtracted off the mean. Now, what happens is, in practice, for us, right, even if you have some random process with non-zero mean, right, we can always subtract off the mean and make it a zero mean random process. So now most of the or all of the random variables that we deal with, random processes, will have zero mean. Okay. If let's say you find that something doesn't have a zero mean, you can always subtract off the mean and deal with a zero mean process. So typically I'll assume that in our case, all of our random processes will have zero mean. Now this non-zero mean can be dealt with separately. Okay, again I'm talking about circuit analysis. So we can always take something that doesn't have a zero mean, subtract off the mean and make it something which has a zero mean, and then deal with only zero mean random processes. Is this okay? And the part that is non-zero, that can be dealt with separately. That is like DC, as we will see later. Okay?
So when you wrote lowercase y equal to lowercase x minus e to lowercase x, each lowercase means the exact value of the random process.
Yeah, actually I should have written the process. Yeah. So what he is meaning is this. Okay. So now there are other measures. So that is known as the mean, and then you have the variance. That's basically I think this is it. So you first subtract off the mean and then find the average square over the density function. Okay. So this gives you the variance, and it's usually denoted by sigma x square. Okay. Now this we will see later. This is a measure of how spread out the distribution is around the mean. Okay. So because you are subtracting of the mean and then you are squaring it. So that means that basically if something is far away from the mean, it will get a large weight. Whether it is far on the left side or the right side, it will get a large weighting, right? Because you have square of this one. And if it is close to it, you will get a small weight. So if this number is large, so that means that the distribution is kind of fat. It's spread out broadly around the mean. And if it's very narrow, that means that basically everything is concentrated near the mean. This is okay. So that's the meaning of this variance, and that's why the term variance also. It basically tells you how much things vary far from the mean. Okay. So these are, and there are other like higher order measures that we won't have to deal with, but essentially mean and variance are what we want to know. And in most of our practical cases, the mean itself will be 0, but basically it's the variance that we will want to find out. Okay. We'll see how this is useful and what we can, in which calculations this becomes useful. Okay. And the square root of this, which would be the sigma x, this is known as the standard deviation. Okay. And like I mentioned earlier, this expectation this is basically an operator that you will come across very frequently when you deal with random variables and random processes and so on. What does this mean? Expectation of whatever it is, let's say whatever quantity this is, some f of x, it's basically you take this, you weight it with the probability density function and then integrate it over the whole range. Okay. So the mean is when mean is just the expectation of x and the variance is expectation of what? X minus a of x. Yeah. Okay. Now if it is 0 mean, this will be the same as expectation of x square. Okay. So these are essentially what we have is that we don't know the value of anything exactly, but if you plot the distribution, they will have some, if you look at the values at a particular time instant, they will have some distribution. And we can get some, we of course know the probability density function itself. And then, see, if you had a deterministic signal, you would say that at, let's say time 1 second, it has a particular value. That is what we cannot do with these random signals. So instead, we can first of all plot the probability density function at t equal to 1 second. And also you may want to have even more compact descriptions of it. So we just look at the average value and the variance. Okay. So there are basically some numbers which kind of compactly describe what the signal looks like, sort of. You don't know the signal value again, but you have some description of signal at t equal to 1 second, 2 seconds and so on. Okay. Now again, if it's a stationary process, then this mean and variance will be the same at every instant of time. Okay. And if it's a non-stationary process, it will be different. If it's a cyclostationary process, it will be different over one period, and then at the same periodic repetition you will see throughout. Is this okay? So now these are again there are higher order measures which you will see if you are taking a course on random processes and so on, but mean and variance are good enough for us. Okay. Now of course, whatever I said with continuous time signals also applies to discrete time signals, that whether it is continuous or discrete time has no relevance here, because here also you can look at the distribution at this instant and that sample and so on. For each one you will have some probability density function, and from that, for each one you can calculate the mean and variance. Just like in the continuous time case, this can be stationary, so that means that mean and variance are the same regardless of what n value you take, or it could be non-stationary, which means it will be different, or cyclostationary, that means it is different for some number of samples and the same variation repeats for the next set of samples and so on. There is periodic variation of mean and variance. Okay? Is this fine? Now these are basically measures taken across the ensemble. Okay? And then there are other familiar measures, that is, which is taken across time. Okay? Firstly, I can take the time average of the signal, that is, for each instance I can take time average. Simply means this is the time average of x, but then this is not a periodic signal. So typically what you do is you take the time average, but with this period going to infinity. Okay? What is this called? This is something familiar to you, right? What is this thing called? If x of t is a signal, what is this thing? This is the DC value of the signal, right? Or you can also have the mean square value, which is okay. So these are measures that you would use for any signal that is varying with time. Okay. Now again, a lot of times we will be dealing with zero mean, stationary processes. Then and it also happens that in these cases the time average of the DC value will be 0 and the mean value is also 0, and the variance will be the same as mean squared value and so on. Okay. So that means that, see, these are two different things. One was you had a distribution, at each instant of time you had a distribution of values and you were looking at its mean and its variance and so on. And the other one is each instance of this random process varies in some way as a function of time, and you can take its DC value and its mean square value and so on. So, and there is a class of processes which are known as ergodic processes. Again, those of you who are familiar with random processes know this. For this class of processes, so whether you take the average of the distribution at a certain instant, or whether you take the average across time, which is the DC value, they will be the same. Similarly, whether you take the variance, which is basically a measure of this distribution, or whether you take the mean squared value, that will be the same, and so on. Okay. Now again, we will encounter some processes that are not ergodic, but by and large we can assume this to be true. Like I said, in our case, firstly we will be dealing with zero mean random processes. So this ergodic process for us in practice means that the variance is the same as the mean squared value that you calculate across time. Okay. Is this fine? So essentially what it also kind of means in a way is, I took this some time instant t naught and then looked at the values of x1, x2, x3, all these different instances of random processes at this time instant, and then plotted the distribution, okay, the histogram or the probability density function, however we represent it. Alternatively, I could have done this, that is, I sample this here and here and here and here and so on, okay, across time. I sample just a single instance of the random process at many instances of time and then plot that distribution or histogram or however I choose to represent that. I will get the same, right? That's essentially what is happening. But this is not necessarily true. In fact, we will see one particular important case where this is not true. But for many of our cases, this is true. That is, what this means is that, let's say yesterday I said that a resistor has noise. So you can have like a million people doing this experiment and looking at the resistance values, the noise values at a particular instant of time, or you can just do one experiment and then you can take million samples at different instants of time and plot the distributions. They will be the same. Okay? Is this fine? Any questions? Now when describing these things, I will vaguely say things like million and so on, but all these will have infinite number, right? And in time or in instances, you have to look at essentially an infinite number of things, but while describing, I will say some large number that comes to my head. Okay? Any questions so far? Ergodic, so far as I know, basically the distribution across the ensemble and across time will be the same. But I think there are proper serious definitions of this that you can look up. So essentially the mean square value is the same as the variance for a zero mean process, that is ergodic. Which one? I'll have to look it up. Yes. Yeah, I'll have to look that up. Any other questions? Now, this just tells you some sort of aggregate measures, right? That is, this mean value and the variance are like the mean value and the RMS value or the mean square value of deterministic signals. Okay? So, they give you just single numbers, right? For instance, what I mean is, you know that the signal that is coming out of this outlet, what kind of signal is that? The signal that comes out of the electrical outlet. Huh? It's a sinusoidal signal. What is the value? You hear some 230 volts. Okay. So you just give it a single number, 230 volts. What number is that? What is that 230 volts? It is the RMS value. Okay. So now, when you say it's a 230 volt outlet, you just know that it is 230 volts, and for some applications it is okay knowing that single number. For instance, if it's a 230 volt RMS AC or a 230 volt DC signal, if you stick a light bulb to it, it will glow with the same brightness, right? Because what is RMS value after all? It is like, it's a measure of heating power, right? So, the mean square value of the voltage divided by the resistance is the power dissipated in the resistor. So, in that sense, like anything that comes out with a 230 volt RMS is the same. But we know that the signal is not the same, right? You also have some description of how the signal is varying with time. In fact, already some of you said that it is a sinusoid. So, similarly, for random processes, we need to have some measures like that as well. You understand what I am saying? So, these are mean value and the variance are single numbers that do say something about the random process. But in addition to this, just like we have the waveform or its Fourier transform for deterministic signals, we need to have some measures that will tell you how rapidly the processes are varying. Okay? So that's what we do, right? For signals, we can either describe the signal itself as a function of time, or we can tell you what its Fourier transform is. And looking at the Fourier transform, you can also tell whether it is varying rapidly or slowly and things like that. Okay. So essentially the Fourier transform, if you have only a sinusoidal signal, the Fourier transform will be an impulse at that particular frequency. By looking at that frequency, you can say, you have an idea of how rapidly it's varying. Okay. And the Fourier transform in general doesn't have to be an impulse. It can also have values over a continuous set of frequencies. Again, by looking at that, you will have an idea of whether it is broadband, that is contains a large set of frequencies, or a narrow band signal and things like that. Okay. Similar things we will need for random processes as well. Okay. Any questions? So for that, what is done is the following. You use a measure called autocorrelation. Okay. Again, I'll try to just give you an intuitive feel for, I'll give you the definition and a feel for why the definition is useful. Okay. So you have different instances of the random process, and knowing exactly how one instance is doing is not very useful, because every instance is going to be very different. Okay. So now what I said was, we need to have an idea of how this random process varies as a function of time. So again, like I said, it's not useful to look at a single instance. Of course, you can even describe it like completely at every instant of time. That is not by itself a very useful thing, because this could have some negative value there, that could have some positive value there, and so on. Okay. So what you use is a different measure, which is called the autocorrelation function, and it is defined like this. Okay. You can use t plus tau or t minus tau, it doesn't matter. Okay. I've already assumed that it is stationary, that is, it will have the same distribution at every instant of time. Now again, this definition is quite easy to understand, and I think you are also familiar with autocorrelation of a deterministic process, right? It's the same definition that you have, isn't it? Have you heard of autocorrelation? Everybody? Yeah, where? What is the definition? What is autocorrelation? Yeah. So you basically take, in this particular case, you multiply the signal by its shifted version and take its expectation, which means okay. So now it will be in general a function of both t and tau, and in stationary processes it will be a function of only tau. But anyway, what I want to explain is what are we getting out of this. So essentially you look at the value of x at a certain instant, and then what's that? Integral will be over. What's that? Yeah. No, this is correct, right? Yeah, this is correct. This is not the deterministic autocorrelation function. Okay. So what you are looking at is the following. So you look at a particular instant t, and then it has some value. Okay. And then you go a certain interval tau away, Okay. So this is t plus tau, and then you see, you take the product of these two. The idea is the following. I mean, at each instant, of course, the process can have a range of values and it has some distribution. Okay. Now, if over this time interval tau, the process doesn't vary too much. Okay. So let's say it is slowly varying. So let me write another set of processes which are also random, but it could be more slowly varying. Okay. Or maybe I'll take some instant of time or the separation between instants that are close to each other. Okay. Essentially what this expectation does is, let's say over this interval tau, the signal doesn't vary too much. What will happen is these two values will be close to each other. You don't know each of these values, but they will be close to each other. Okay. So that means that you will end up with, whether it's positive or negative, you will end up with a positive value here, and you will get a large correlation. Okay. On the other hand, let's say over this time, it varies quite a lot. Okay. What happens is that, so here it is positive, but at this instant it can be anywhere from negative values to positive values. Okay. Think of distribution like this, right? It can have any negative value or positive value. So then what happens is when you take this product and take the expectation, you will end up with 0. Okay. Because the values here are not correlated with the values there. That's the idea. Okay. On the other hand, if, so again, it's hard to draw these things, but you understand by looking at this plot. So let's say, over this interval tau, the random process doesn't change too much, then clearly you will end up with, whether x is 0, while you don't know what x is, you will end up with only positive numbers inside the expectation. So that means that you will end up with a large value. Is this okay? So on the other hand, if it varies quite a lot, so that all the correlation is lost, that's the term that's used. So then x could be positive or negative, but the point is here, starting from any value, this could be any other value also, so that when you take this expectation, you will end up with 0. Okay. So we'll see examples of this. This is the measure that is used to kind of figure out whether the random process is varying quickly or slowly. Okay. So again, these definitions and rigorous calculations you will see in courses that deal with probability and random processes and communication systems and so on. But what I am trying to give you is a feel for these things, and especially for circuits, this is the kind of some intuitive understanding that we need. You will need to know how to calculate this, but actually it's very infrequently that you will calculate the autocorrelation of some function from scratch. Okay. So you will have some standard set of things that you do with this, but you need to know why we do any of these things. Okay. So this is a sort of time domain measure of whether it's like random processes varying slowly or rapidly. In case of deterministic signals, you don't need any of this. You know what the signal is. You can look at it and say whether it is varying slowly or rapidly. Of course, when I say things like slowly, I have to also specify the time scale. Okay. So let's say over a period of 1 microsecond, whether it's varying a lot or little, you can just plot the signal and look at it. In case of, I mean, from the definition of the signal, you know when you have a deterministic signal. Whereas in case of a random process, it's not clear. I mean, you don't know the value of the random signal at every instant of time, right? That's the idea. That is the randomness. But what you do is essentially you look at this is a measure of how much the signal is changing over that interval of time. Okay. Hopefully these plots kind of make it clear. If it is not changing too much, you will end up with a positive number. But if it is changing quite a lot, you will end up with a 0 expectation or something that is very small. Okay. Is this fine? Any questions here? So we will continue from this. And similar to Fourier transform, there is a frequency domain measure also of this. So that is also very useful. Frequency domain calculations are quite useful in practice in many contexts. So we will look at those things and relate them to other stuff. And from then on, I mean, we will just do the calculations, the rigorous definitions, etc. You can find in probability and random processes textbooks. Okay.